This is the second vodcast on Einstein's special theory of relativity for Physics Unit 3 and 4, Study Design. So in this episode we're going to be covering Einstein's two postulates for the special theory of relativity. And you can see our goal there on the page. I'll point out that this is the first vodcast which is directly addressing one of the dot points in the study design. So in the study design it does explicitly say to describe Einstein's two postulates for his theory of special relativity. So this is addressing that specifically. Now I want to just start by kind of recalling where we were with the last episode, where we were able to show that the velocity of an object, in particular a ball, was different depending on our frame of reference. So we had a situation like this where someone was standing on a platform, stationary on a platform, a train was moving past with a velocity relative to that platform, which we were calling VA relative to C, and then there was a ball within that train which had a velocity, so that's VB relative to A. And so we said that the velocity that the person on the platform would measure would be different to the velocity that the person on the train would measure. Now there might be a natural instinct for us to have a feeling of, well, which one is right? Which of the two measurements is actually the correct measurement? And I think the natural instinct might lead us towards thinking, well, the person on the platform is the one who's actually correct. They're making the correct measurement because we know they're not moving. But of course we can quickly prove this to be false. We know that this situation it's happening on Earth, right? So on our blue planet, on our red country. My quick drawing skills, and our planet is moving very quickly relative to a much bigger object, which of course is the sun. And so we say that, well, we know that if we're actually measuring the velocity of Earth as a whole relative to the sun, there's a huge velocity there. So there's no way in which we can really claim that this person is more not moving, or is in a more correct sense not moving than the train is. It's just our personal bias, but it's not really in any way correct. So we need to move away from this notion, which is a natural instinct of thinking that there is a more correct inertial frame of reference. So the first thing that comes out of this is we need to understand there's no universal coordinate system. I mean, we can then take the sun and say, well, the sun is moving within a galaxy, and the galaxy is moving within the universe relative to all sorts of other things. So we need to just remember all motion is relative, and there is no universal coordinate system, which means that all inertial reference frames are equally valid. So to come back to this example, what that's saying is that the person, Amanda, in our train, the measurements that she's making are just as valid as the measurements that the person on the platform is making, and there is no sense in which this person is more at rest or not moving. So this gets us straight away to the first postulate of Einstein, so he put it in a much more eloquent way. So Einstein's first postulate is this: the laws of physics are the same in all inertial frames of reference. So it's just basically saying that no frame of reference, or no inertial frame of reference, is more correct than another. Now this word's important, inertial. If we have frames of reference which are non-inertial, meaning that they're accelerating or not moving at a constant velocity, then we do have a difference. We can say that measurements in one frame of reference, i.e. a non-inertial frame of reference, are in some senses different and perhaps not as correct as measurements in an inertial frame of reference. But at this stage we're only considering inertial frames of reference, and in that case they're all as good as each other. Okay, so from that then we can move on to talking about speed. So when we talk about speed, then it raises the question, well, what reference frame are we using? We talk about speed all the time. So we talk about it in the sense of, for example, a car. My excellent drawing of a car driving along the road. And for example, an everyday use of a speed might be saying the speed limit on that road, which might be 60 kilometers per hour, for example. And we don't usually find ourselves having to say what that speed is measured in relation to, and that's because it kind of becomes obvious that the speed of the car is determined by its interaction with the road. The thing that's able to make the car move is the fact that it's in contact with the road. If we lifted it off the road, then of course it wouldn't be moving at all. So the tyres need to be making contact with the road. And so there is some sort of obvious connection there, that the speed we're talking about is a speed measured in the frame of reference of the road. And so that's what 60 kilometers per hour is referring to when we talk about a car. Another, I suppose, common example might be to consider a plane. So if we have a, well, let's got a pretty wicked jet. And of course it's moving very quickly. But when we talk about the speed of different planes, again, we don't often say what we're measuring that speed relative to, but then again we need to think, well, what's the thing that the aeroplane is depending on for its motion? In this case, it's not depending on a road. What an aeroplane depends on is the air around it. So normally when we talk about the speed of a plane, we're talking about relative to the air. Right, so here it was relative to the road, and here it's relative to the air, which, and this has direct consequences if you've ever been delayed getting a plane, and it will often be because there's a headwind. In other words, the air is moving opposite to the direction you want to go. So it's a little bit like being in a train and you're trying to go to the right, but the train's going to the left, and you're fighting against that. Or if you've ever been, I guess, silly enough, if you will, to try and climb an escalator that's moving downwards, and you're fighting against that escalator that's going downwards, and you're trying to get up. It's kind of the same if you're going against a headwind of a plane. So if the plane you're in is going against a headwind in the air. So the speed is measured relative to the air. And then another thing that we can talk about and is particularly relevant here is sound. So you might remember from junior science, or perhaps the way everybody talks about one of the biggest problems with Star Wars is the fact that apparently you can hear the explosions in space. But we know that we can't. There's a lot more problems with Star Wars than that, but that is one of the physical problems. We couldn't hear anything in space, couldn't hear any explosions because of the fact, of course, that there's no air. So the thing that sound moves through is always air. And a good example of this, if you've ever seen a fighter aeroplane or any aeroplanes that can go faster than the speed of sound, you will see the plane reach you before you hear it. And so the reason for that is, let's just imagine that the sound is starting at this point. Our plane's moving to the right. Here you are observing the aeroplane. And so the plane is making a lot of noise, obviously, because of its engines and so on. And so just imagine that this is a sound wave that's moving to the right. Now, sometime later, our aeroplane aeroplane's looking worse and worse. Sometime later the aeroplane's here, so the aeroplane's right ahead of you and you're looking right up at it, but you haven't heard it yet because in that time the sound, which is actually travelling slower than the fighter plane, has only reached, say, this point. So the sound wave that came from the plane when it was at this point is now behind it, and so you haven't heard it yet. So the key idea here is that the sound is not measured relative necessarily to this person. It's not measured, certainly not measured relative to the plane, because the plane is actually moving ahead of the sound wave. The sound is measured relative to the air, because that's the thing that it must move through. And so you might remember from junior science that we called this a medium. Any wave has to move through a medium. Well, most waves, and we'll get to that. And in the case of sound, that medium is the air. Usually. It can move through water and that kind of thing, but in our day-to-day experience, we're usually talking about sound moving through the air. So you can see that when we talk about speed, we're usually talking about it relative to some given thing, which is usually sort of implied in the circumstance. So it's sort of obvious, for example, that we know a car its speed should be measured relative to the road and not measured relative to another car that's moving next to it or something like that. So if we're happy with that, then we need to think about something where it gets a little bit confusing, and this is where special relativity does start to get very interesting. So that idea is light. So in all of the examples I just gave before, it was kind of obvious to a greater or lesser extent what that speed is measured relative to. But in light, or in the case of light, it's really not obvious. It has no particular connection with the earth, it has no particular connection with air, it has no particular connection with anything. So if we want to measure its speed, then what exactly are we measuring it relative to? What's the frame of reference that we're measuring it relative to? Well, there were suggestions that light being considered a wave, and in later areas of study we'll talk about whether or not we should consider light to be a wave, but there's lots of reasons why we can say it should be. Then it was argued that just like sound moves through a medium being air, maybe there's a medium that light moves through called an ether. So this word was sort of invented to cater for this situation. Maybe there's a thing called the ether. Well, basically, and I'm not going to go into detail of the experiments for this now, but experiments were carried out to show that that's definitely not the case. There is no ether. So we can cross that off. If you're interested, look up the Michelson-Morley experiment. It's in your textbook, and there's plenty of descriptions online, videos and that kind of thing. But I'm not going to go into that now because it's not something you explicitly have to cover in the study design. But if you're happy to take it basically as fact at this stage, that what this experiment measured was that in different frames of reference, the speed of light was measured to be the same thing. So the Michelson-Morley experiment was not done with a train, but the result is equivalent to the example that I'm going to give you here. So let's say that we consider, similar to the ball that we were looking at in the previous episode, we have a train that's moving to the right, we have person A standing in that train, and there's a light bulb. And that light bulb gives off a pulse of light, it flashes. And the light bulb's at this position, so you can see it's, say, position 2 at this point in time, and we're just calling this t equals 0. And our train is moving relative to the platform, which is relative to this person C standing on the platform. So at this particular point in time, the light bulb flashes, it's at a position 2. Both person A and C agree that it's at that position. Now what happens if we look a little bit later? Well, let's say that the train's now moved some distance to the right according to person C, and as it's moved, so this is because of this relative velocity, so we can see that it's moved to the right 3 units, 3 centimeters if you like. We also know that the pulse of light or the flash of light has moved away from the light bulb. Now it's moving in all directions, as you can see here, but for simplicity we'll just look at it going in one direction. So we'll look at its movement to the right. So let's just say, for the sake of argument, that in this time, in this 1 second, the light has moved 4 units to the right. So 1, 2, 3, 4. So let's just say that this is our flash. It's kind of reached that point as it moves to the right. Okay. So person A in the car measures it to be at this point. And where it gets really tricky is that at the same time, because they have to measure the speed of light to be the same, person C will agree that it's moved 4 positions to the right. But that's 4 positions to the right from his point of view. So it started here, the light bulb was in position 2 originally, and it's moved 4 positions to the right, the flash, so 1, 2, 3, 4. So he says that the flash is here. Now, just to be really clear, this is the same flash, but these 2 people are measuring it to be in different positions, because they're saying the speed of light is the same for each of them. Whereas when we were talking about a ball, if the ball was here for person A, then that meant the ball was here for person C. But in the case of light, we're saying that at the same time, the light is here and for person A, and the light is here for person C. That's crazy. It's like light's behaving with some sort of a split personality, and an infinitely split personality, because we could introduce more and more reference frames, and for every different reference frame, they would measure the light to be at a position that is relative to them, means that the speed of light was at that value, but that means it could be in an infinite number of different positions at that point in time. So it's doing something really, really strange, and it seems to almost be a contradiction that it's able to do, sort of be in these 2 places apparently at the same time. But this is what Einstein's second postulate is, and it's backed up by evidence. So it's very sound theory now. But basically everybody always measures the speed of light in a vacuum, and we call that speed of light c to be 3.0 times 10 to the power of 8 meters per second to 2 significant figures. It's actually slightly less than that, but to 2 significant figures. And so the way that Einstein put it, the speed of light has a constant value for all observers, regardless of their motion or the motion of the source. Now, what the effects of this are, because there's clearly going to be some strange and interesting results that come out of this, what the effects of this are we'll look at in the next episode. But perhaps a clue to trying to resolve this situation is, I kind of used a term incorrectly here where I said at the same time the light is in these 2 places. As we move forward, we're going to have to start to throw out this idea of things being at the same time. So just what it means for something to occur at the same time, in other words, be simultaneous, no longer fits in with our intuitive sense of that idea. So that's something that we'll be talking about in the next episode, which will be on the relativity of simultaneity. Again, if you have any questions or comments, please put them in.